Hello, so this is another class and we are discussing representations of finite groups. Okay, so let me try and share screen. All right, so what we did last time around was look at I told you about, firstly about the group of permutations S3, and then uh, I showed you two separate ways in which this could be written. And you're supposed to, actually, very important thing is you're supposed to complete the multiplication table for S3. That was homework that you should do. Then we went to speak about, you know, matrix representations of a group. And I told you that these were n-dimensional, an n-dimensional matrix representation was of a group. You could have the representation of an element of a group G. This was given by a transformation dg of this n-dimensional complex vector space onto itself. And so if you know this for the transformation, so this is known once we know the transformation of basis of Vn. Okay, then we went on to try to understand the word representation for S3. And I showed you that these sort of operations, which, for example, the 1-2 operation exchanges 1 and 2. So this would be given by a matrix like this, which took the vector ABC to the vector BAC. Okay. Um, Equivalent. So similarly, you could find out what the other other elements of S3 were. And you could see for yourself that when you looked at the multiplication of two elements, the group the group property will be obeyed. So dA, the representation of the eighth element and the representation of the b8th element, when you take the product of them, it will become the representation of the ab8th element. Okay. This is something that you were supposed to do. Hopefully, you have done it. Otherwise, I mean, you would find time to try and do it in a bit. And so what we want to do today is I'm going to tell you a little bit about other representations. So we start off with something called the regular representation. So the regular representation, we call this dr of a finite group. In this, the matrix which represents a group element is defined in very close analogy with the operation of G on the elements of the group. The dimension of the vector space, in the case of the regular representation, is equal to the order of the group. And what we will see, so the orthogonal basis elements EI are related to the group elements GI of G. Okay. So we are going to first define it in an abstract way. So the operation of the matrix, which represents the transformation GK on this basis vector EJ, is defined by something like this. Okay. So dr on GK, so this is the regular representation of the GK, which is the element of the group. This is acting on this orthogonal basis element EJ, and that gives you this sum over I 1 to P. So P, as you would remember, is the order of the group. and there is this, delta function, and you have EI cap. Okay. So now what is this? This particular thing is, so the delta of gk into gj, comma gi is 1 if gk gj is gi and 0 otherwise, like a usual regular delta function. This might look very abstract, so let's try to understand it in terms of the thing that we are looking at again and again. So the word representation, right? In terms of S3, okay? So let's look at this. So we'll start off with the we'll start off with S3, and since S3 has six six elements, the dimension of this representation is also going to be 6. Okay. Now let us look at the representation of G3. Okay. G3 is, remember, this permutation of 1, 2, 3. Okay. Now, if this is something that you guys would have done, or you would be sort of doing, you will see that the multiplication table of S3 gives you G3 G1 equal to G3, G3 G2 is equal to G1, G3 G3 is equal to G2, G3 G4 is equal to G5, G3 G5 is equal to G6, and G3 G6 is equal to G4. Okay, so of course all the elements will have to be, you'd get all of them back. So now let us look at this. Okay, so now what we want to do is we want to find out dr of G3. Okay, now this is going to operate on EJ. Let's start off with E1 first. Okay, so what is this? So if we have E1, so let's do this. Let's just before we do anything, let's try and understand it. So dr of G3 acting on E1. Okay, so this is what? This is summation I equal to 1 to 6 now, because P is 6, delta GK. So this is G3, and GJ is GI. GJ. So J is what? J is going to be. So we are looking at E1. So J is 1, and this is GI and summation EI, right? EI. Now G3 G1. What is G3 G1? G3 G1 is equal to, as you see here, G3 G1 is G3. Okay. So what do we have here? So this has to be equal to summation I equal to 1 to 6 delta of G3 GI EI. So delta of G3 GI is then, of course, so G3 has to be equal to GI. So I is equal to 3. So this has to be equal to E3. Okay. So what have we got? We have dr of G3 acting on E1 is E3. Okay. Similarly, you can get it for the whole, you can get it for the entire, for all of these things. So you can get it for E1, you can get it for E2, and so on and so forth. Let me just erase this for the moment. Very good. So let's do this. Let's see. So now what we find is dr of G3 is E3. Similarly, you can do gr of E2. You'll find this is E1. Gr of E3 will be equal to E2, and you can get the rest of these things. And so once you see this, then what you'll have is you can find out that this particular object dr of G3 is going to be given by a matrix like this. How do you get this? So dr, so this is going to be, so what do you want? You want to find dr of G3, and so this is going to be E1 dot 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 E6, and this is going to give you what? This is going to give you E3, E1, etc., right? And up to E4. So the matrix which does this is going to be this matrix that I wrote down out here. So this is going to be the representation, the regular representation of G3. Okay. Similarly, you can find out all the other matrices in the way that I've just shown you. This again is going to be homework, and I urge you to go and do this as fast as you can. Okay. So homework is that find the other matrices. So what have we got now? So we have looked at this thing called the regular representation of S3, which is something which gives you a 6-dimensional representation. Question is, so what did we do earlier? We found something which was a 3-dimensional representation earlier, right? So we found this. So this was what we call the word representation, and this was like a 3-dimensional representation. Okay. Now we've found something which we call the regular representation. This is a six-dimensional representation. So can we find more? Yeah, of course we can find more. So let's show you an example of something which is again going to be a lot of fun. So let's look at the symmetry group of a triangle. Okay. We are going to look at transformations in a 2D plane of the 2D plane into itself, which leaves invariant this particular equilateral triangle. Okay. So what is this? So as you can see, you can rotate this equilateral triangle by an angle of 120 degrees, and things are going to stay the same, right? So what is 120 degrees? That is 120 degrees, just 2 pi by 3. So this is what is going to keep this this triangle the same. Okay. So you can do this, you can rotate it around and so on, and then it's going to come to this and ultimately get here again. So the triangle goes into itself. Okay. So it just rotates. If you rotate the system by 120 degrees, it stays the same. So what is something that is going to rotate? So if you have your axes which were like this, you can rotate each of them by 120 degrees, and then this thing stays the same. Okay. So the operation, if you will, is going to be an operation of rotating it by 120 degrees. Now, this is something that we're going to learn, also later. So if you want to represent a matrix R, which has, this is something that you guys know well, okay? So if you have a vector which is X, it's, it's XY, and you want to rotate this by an angle theta, then what do? You have cos theta minus sine theta, cos theta into xy, right? So this is just x prime is equal to x cos theta plus minus y sine theta, and y prime is equal to x sine theta plus y cos theta. So this is this is how you do it. So now theta here is equal to 2 pi over 3. Okay. So now let's do this. So once you do that, so this rotation by 120 degrees then boils down to something which is, so r is given by minus 1 minus root 3 over 2, 3 over 2, and minus half. Okay. So r squared is going to be a rotation by 240 degrees. So you can also do this, and you'll find that r squared is this. This also, if you rotate it by 120 degrees, so this also comes back to itself. This sort of equilateral triangle comes back to itself. So this is this, and r cube, as we have been saying, r cube is obviously equal to 1. So that's great. So that's symmetries, and there's another one actually as well. So if you look at the x-axis, so this is the x-axis, and if you look at reflections around the x-axis, that is also a symmetry, right? So that is just, again, in that case, I mean, theta is, so then what so E1 was going to map to E1, but E2 is going to map to minus E2. Remember that yeah, so E1 maps to E1, but E2 maps to minus E2. So the matrix that is going to represent this is P. P is going to be, so this is what you have to, so P acting on E1, E2 is going to be equal to E1 minus E2. So this is what this has to be. So this means that P has to be of this form. Okay, very good. Now notice the following. There is, so now you have these two separate things, right, which are both symmetries of this this group. So you can sort of try and, I mean, also compose them, and that will also remain a symmetry of this equilateral triangle. So you could have PR, so you multiply P with R, that also remains as symmetry. You'll also have PR squared, so which is this object. So now we have six invariant, six invariant elements: the identity, R, R squared, P, PR, PR squared. Now suppose you indicate the corners of the triangle by A, B, and C. So this, I mean, invariance operations essentially just mean a rearrangement of A, B, and C. Okay. So for example, if you were to rotate this by 100, so if you were to rotate, I mean, ABC by 120 degrees anti-clockwise, then you're going to get, BAC. I'm sorry. So not BAC, but what am I doing? So I'm rotating this, and what I get, so I rotate this anti-clockwise, yes. And so what do I get? I get BCA. Okay. So you should, I mean, count things in this way. So so you get BCA. So you see that this is just turned. So this goes here, this goes here, and this goes here. So this is BCA. So this particular thing represents the, the operation that we were also looking at, this operation 132. So you can see that, for each of these things, again, this is something for you to check, that each of these things is going to represent a particular element of S3 again. So what we have is that now what we see is that we have got another representation of S3, and this representation of S3 is a two-dimensional representation. Okay. Another homework for you guys is, finding the full two-dimensional representation of S3. What are these things? If this is 132, what is R squared? What is P? What is PR? What is PR squared? Find these things out. Okay. All right. So moving on, let's learn a little bit more. So there is, for each group, there is a trivial representation D1. And in this, every group element is actually represented by 1. Okay. So this is trivial, and you would be able to see that this satisfies all the requirements of a matrix representation. Okay. For these permutation groups Sn, there exists another one-dimensional representation. We'll call it D1 primed. And in that case, we will have that D1 primed is 1 for even permutations and -1 for odd permutations. So this is something that you would, again, this is something that you can see. And there could be other groups which have other sort of complex one-dimensional representation. A3, for example, which is the subgroup of the even permutations of S3, that could have, that could have some particular representation that I highlight out here. And there could also be the these would be non-equivalent representations. This could be another one. Okay. So these are more about representations that we have learned now, and we will actually go on and try and learn a little bit more.